Hello, all of you. Welcome to the next subtopic of semiconductor chapter. And in this subtopic, we are going to learn about the common emitter configuration of bipolar junction transistor. We have understood the introduction of bipolar junction transistor in the previous session. And now we are going to learn more detail about this common emitter configuration because this is the only configuration in the syllabus of 12th standard. If suppose you do electronics engineering or some other part of engineering, then different types of configuration it will be there in your syllabus. But in 12th standard, only common emitter configuration is there. Common emitter configuration, as the name suggests, the emitter will be common between the base and the collector. So the base will be the input side and collector will be the output side. And we can say that base will be the input side and collector will be the output side, and we can say emitter it is common between base and collector. So this is the circuit diagram, the overall circuit diagram. This Vin is the input voltage, Vin is the input voltage. So you can say that the input voltage is applied to the base terminal. Input voltage it is applied to the base terminal. IB is the current, base current. We all know that IB it is very less. It is actually 5%. So you can say it is in microamperes. The IB current it is in microampere. Okay. While this is the collector and this is the emitter side. So emitter it is connected to ground. Emitter it is connected to ground. That means emitter it is common between base and collector. So that's why the name it is common emitter configuration. The collector plate it is connected to a power supply which is called as VCE. That means the voltage across collector and emitter. While this is called as VBE. That means the voltage across base and emitter. This is the load resistance RL. So whatever is the output we are getting, the output will be across this resistor RL. Okay, so this is the Vout. Vout is nothing but IE into RL. As per the Ohm's law, voltage is equal to current multiplied by resistance. So current flowing here it is IE. IE is the emitter current. IC is the collector current. Okay, and IE into RL. This is the voltage, output voltage. So this is a common emitter configuration. The input signal is applied between the base and the emitter, while the output is obtained between the collector and the emitter. So you can say that input in on the input side, emitter is there. On the output side, emitter is there. That means emitter it is common between input and output. That's why it is called as common emitter configuration. So this configuration shows the highest current and power gain. So if you consider the common emitter configuration, you will be getting highest current gain, also highest power gain. Why? Because the input impedance is low. Input impedance is low. Why? Because it is forward bias. So this is which type of transistor? This is NPN transistor. NPN transistor, how we can say? Because the arrow is towards the emitter. So negative, it is connected to the negative terminal. The negative is connected to positive, while the negative is connected to the positive terminal of the emitter like this, and here it is positive is connected to negative and negative is connected to positive. This is just the power supply connection. Okay, just the power supply connection, and not properly it is maintained. Okay, actually this should be like this. Okay, and this is now forward bias. Okay, and this is positive connected to negative, this is reverse bias. Okay, so since the input it is forward bias, that's why input impedance is low. Input impedance means input resistance is low. Why? Because it is forward bias and that is connected to forward bias PN junction, while the output impedance is high. Why output impedance is high? Because it is connected in the reverse bias condition. So negative connected to positive, positive connected to negative. So this is the reverse bias condition. So this is reverse bias. That's why output impedance is high, while input impedance is low. Okay. Common emitter configuration, current gains in transistor. So there are two terminologies, alpha and beta are the two current gains in the transistor. The first one is called as alpha. So the ratio of collector current to emitter current. The ratio of collector current to emitter current is called as alpha DC, which is nothing but you can say um, the 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 amplification factor between the input and output. So this value is always less than one. Is always less than one. Alpha is always less than one. Alpha is always less than 1. Okay, alpha is always less than 1. Why? Because why alpha is always less than 1? Because we all know that if IE it is 100%, so how much is the current through collector? It is 95%. Okay, so that means the alpha value it is between 0.9 to 0.95, 0.95 like this, 0.98 like this. So it is always lesser than 1. Why? Because the denominator it is greater than the numerator. That's why alpha is always less than 1. The next amplification factor, the current gain is amplification factor. So the ratio of the collector current to the base current, that means IC divided by IB, it is called as beta DC. So this beta it is called as current amplification factor. Current amplification factor. Amplification factor. Current amplification factor. So the current amplification factor it is nothing but the ratio of IC divided by IB. Okay. So IC here it is 95 percentage and IB is only 5 percentage. That means beta is always less than 1. Beta is always greater than 1. Sorry. It is always greater than 1. Beta is always greater than 1. So beta is always greater than 1. This indicates that this amplification factor it is always greater than 1. That means beta value it can be between 25 to 100 like this. So this depends on the quality of the transistor, which quality transistor we are purchasing. So in that case, let's suppose we are purchasing a transistor. Now what you know, there will be the value of alpha and beta. So there will be a value of alpha and beta given to you if you are purchasing the transistor. Okay, and these two are called as current gain. So this alpha it is called as IC divided by IE, which is always less than 1, and this beta it is called as IC divided by IB. Okay, which is always greater than 1, because numerator is far greater compared to the denominator. That's why the beta value is always greater than 1. Okay, all of you can pause the video wherever you like and you can write the things, you can complete the things. The next is we'll be looking at the relation between alpha and beta. So here you can say that this current moving is IB and this current moving is IC. Together it is building IE. So what we have is IE it is equal to IC plus IB. IE it is equal to IC plus IB. Okay. So what is common between the two formulas? The common between the two formulas is IC. Okay, remember this. IC is common between the two. So next we are going to derive a relation between alpha and beta. So what is the beta definition? The ratio of collector current to the base current is defined as beta. The current amplification factor beta it is equal to IC divided by IB. While the ratio of the collector current to the emitter current is defined as alpha. Then alpha is called as IC divided by IE. Okay. So I can write like this. We know that IE it is equal to IC plus IB. IC plus IB. IE it is equal to IC plus IB. Okay. So what is common between the two is IC. IC it is common between the two. So I can say dividing both the sides by IC. So if you divide both the sides by IC, you will be getting like this: IE divided by IC. It is equal to what? IC divided by IC plus IB divided by IC. So IC divided by IC it will be equal to 1. Okay. So therefore I can say IE divided by IC that is equal to 1 plus IB divided by IC. Now what is IE divided by IC? If you see it is IC divided by IB. So what will be IE divided by IC? It will be 1 upon alpha. Therefore, 1 upon alpha it is equal to 1 plus IB divided by IC. Again, this is IC divided by IB, the reciprocal of beta. It is 1 divided by beta. Okay, so suppose we are interested in getting the value of alpha, I can write like this. I will write in some other color. So this will be 1 upon alpha, it is equal to beta plus 1 divided by beta. So therefore, what is the value of alpha we will be getting? Alpha value will be equal to beta divided by 1 plus beta. Okay, so here you can see this 1 plus beta is always greater than beta. So hence alpha is always less than 1, right? Alpha is always less than 1. So given with the value of beta, you can get the value of alpha. Now, if suppose alpha value is given and if we are interested in getting the value of beta, how we can derive this? Okay, so we will consider this equation only. And I can say 1 plus 1 by alpha minus 1, that is equal to 1 divided by beta. So therefore, I can write 1 minus alpha divided by alpha, it is equal to 1 by beta. So therefore, what is the value of beta then? Therefore, beta it is equal to alpha divided by 1 minus alpha. Okay, beta it is equal to alpha divided by 1 minus alpha. Given with the value of alpha, you can get the value of beta. Now, beta is always less than 1, that's why it is 1 minus alpha. So 1 minus alpha, it is always lesser than alpha. Okay, that means beta is always greater than 1. Beta will be always greater than 1. Okay, so this is the relation between alpha and beta. This derivation is not there in the textbook, but it may be asked in the board examination. So I request you all to please note this down. Okay. So this is all about the common emitter configuration, the introduction to the common emitter configuration. The next we will be learning about the characteristics of the common emitter configuration, the input characteristics and the output characteristics. Okay. Thank you so much all of you for paying attention. Keep learning, keep smiling. Goodbye.